Hello everyone. So this is a question from JEE Advanced 2026 paper 1. In the following sequence, Q, R, S and T are the major products. Okay, so we are starting with this guy and we are getting Q, R, S and T. So we have to find out their structures. The correct statements about Q, R, S and T is R. Okay, so few statements are given to us. The chapters involved is hydrocarbons, aldehydes, ketones and carboxylic acids. Okay, so we are starting with a sodium salt of a carboxylic acid. Okay, so this is a sodium salt of a carboxylic acid and this is sodium butanoate to be specific. Sodium butanoate. Okay, and it undergoes Kolbe's electrolysis first. Okay, so we should know that when a sodium salt of a carboxylic acid is electrolyzed, an alkane is produced. Okay, alkane is produced. And if N is the number of carbon atoms in the salt of the carboxylic acid, then the alkane formed has 2 into N minus 1 carbon atoms. Okay, so in our question, the starting sodium butanoate has 4 carbon atoms 1, 2, 3, 4. Okay, so N will be equal to 4 here. So therefore, the alkane will have 2 into 4 minus 1, that is 2 into 3, which is 6 carbon atoms. So with respect to reaction, I can write CH3, CH2, CH2, COO, Na, which is sodium butanoate, and Kolbe's electrolysis. So I'll be getting CH3, CH2, 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 CH3, which is my N-hexane. Okay, then N-hexane is subjected to the second set of reagents, that is V2O5, 500 degrees Celsius and 10 to 20 atmosphere. Okay, V2O5, 500 degrees Celsius and 10 to 20 atmospheres. So we should know that when alkanes containing 6 carbon atoms, when heated to about 500 degrees Celsius under 10 to 20 atm pressure in presence of a catalyst consisting of oxides of vanadium, get converted into the corresponding aromatic hydrocarbon, that is benzene. So that is, with respect to reaction, I can write CH3, CH2, 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 CH3, V2O5, 500 degrees Celsius, 10 to 20 atm, will lose a molecule of hydrogen to give me cyclohexane, which will further lose 3 molecules of hydrogen to give me benzene. Okay, so therefore this is my Q is nothing but benzene. Okay, benzene in the presence of acetic anhydride undergoes Friedel-Crafts acylation. Okay, very important. Benzene plus acetic anhydride, obviously in the presence of anhydrous AlCl3, undergoes Friedel-Crafts acylation. Okay, so with respect to reaction, I can write benzene ring. I will show one H plus acetic anhydride is CH3 C double bond O, O C double bond O CH3, anhydrous AlCl3. Okay, so what happens is this oxygen takes away these electron pairs, so it will have a negative charge, and this carbon will have a positive charge. Okay, so therefore this whole acyl group will go and replace this H, and this H will be connected to this O to ultimately give us benzene ring C double bond O CH3 plus CH3 C double O H. Okay, so this is what we get when we do or when we react benzene with acetic anhydride in the presence of anhydrous AlCl3. Okay, so in our question, we are reacting benzene with phthalic anhydride. Okay, we are reacting benzene with phthalic anhydride, which is a cyclic anhydride. Okay, and it will behave in a similar way to acetic anhydride. That is, with respect to reaction, I can write benzene ring with an H plus phthalic anhydride, that is benzene ring C double bond O, O, C double bond O connected to O. Okay, so this is my Q and this is my phthalic anhydride. So obviously in the presence of anhydrous AlCl3. So this oxygen will take away these electron pair, therefore it will have a partial negative charge. This carbon will have a partial positive charge. Okay, so therefore this carbon goes and attacks our this carbon, and this H will become a part of this O. Okay, so ultimately we will get this guy, benzene ring. Instead of H, we will have, C double bond O connected to this benzene ring. So C double bond O, which is itself connected to another benzene ring. Okay, and this benzene ring will be connected to this C double bond O, and there is an H. Okay, in the ortho position. So therefore, I will have C double bond OH. So this is my R. Okay, then R is subjected to the first set of reagent, that is PCl5. Okay, so R has a carboxyl group. This is the carboxyl group. Okay, so we should know that carboxylic acids reacts with phosphorus pentachloride, that is PCl5, to form acid chlorides by replacement of the OH group by Cl atom. Okay, so therefore with respect to reaction, this guy in the presence of PCl5 will give me benzene ring C double bond O, another benzene ring which is connected to C double bond O and Cl. Okay, then this guy is subjected to the second set of reagents, that is H2PD BaSO4. Okay, so we should know that acid chlorides are reduced to corresponding aldehyde by passing hydrogen gas in presence of palladium catalyst supported over BaSO4. Okay, so this is the famous Rosenmund reduction reaction. So with respect to reaction, this guy in the presence of H2PD and BaSO4 will give me the corresponding aldehyde. So I will get benzene ring C double bond O, benzene ring, and C double bond O H. So this is my S. Okay, then S reacts with NH2, that is hydrazine and heat, to give me T. Okay, so carbonyl group in aldehydes and ketones, important. Carbonyl group in aldehyde and ketones are reduced to methylene group, or they are converted to methylene group. That is, the C double bond O is converted to the CH2 group when heated with hydrazine to form hydrocarbon. Okay, that is, we start with aldehyde and ketone, we ultimately will get hydrocarbons. Okay, so this is the famous Wolff-Kishner reaction. Okay, if we have both an aldehyde and a ketone in the organic compound, so you can see in S we have ketone group as well as aldehyde group. Okay, so if we have both an aldehyde and a ketone in the organic compound, NH2 will prefer to attack and reduce the aldehyde over the ketone, as aldehyde have less steric hindrance and stronger partial positive charge on the carbonyl carbon. Very important. So I will write it down. If we have both aldehyde and ketone in organic compound, NH2, that is hydrazine, prefer to attack and reduce aldehyde over ketone. Okay, so this is because aldehydes have less steric hindrance and obviously more partial positive charge on carbonyl carbon. That is, with respect to reaction, I can write C double bond O, which is connected to benzene ring, which is connected to C double bond O H. Okay, so obviously this oxygen is electronegative, so it will pull these pi electrons to convert them into lone pairs. So therefore it will have a partial negative charge, and this carbon will have a partial positive charge. Okay, so we are reacting this guy with NH2. So I will separate one H. Okay, so this H will have a positive charge and the rest of the molecule will have a negative charge, and in the presence of heat. Okay, so what will happen, this H will go and get attached to this oxygen, and this rest of the molecule will come and get attached to this carbon. Okay, so we will get benzene ring, C double bond O, benzene ring, C is connected to OH, which is connected to H, and it is connected to NH2. So N, which is connected to H, and it is connected to NH2, and obviously this is a benzene ring. Okay, because of the heat we will lose this OH and this H as a form of a molecule of water, so we will get ultimately benzene ring connected to C double bond O, benzene ring, CH. So since we have lost OH and H, so there will be a double bond between C and N. Okay, so we will have CH double bond N, which is connected to NH2. So I will write them like this. Okay, N has a lone pair here. Okay, so the lone pair of electron on the N atom in NH2, that is, these are the lone pair I'm talking about, attacks the electrophilic carbon of adjacent carbonyl group. So this will go and attack this carbonyl group. So this carbon is positively charged, okay, resulting into a 6-membered ring. So because of this attack, we will get benzene ring, C. Obviously, oxygen will take these electron pairs as lone pairs. Therefore, it will have negative charge, and this H will be a part, go and be a part of this O. So therefore I will have COH, benzene ring. It is connected to NH, which is connected to N, which is connected to double bond CH, and CH is connected to this. Okay, so you can see there is a six-membered ring. 1, 2, 3, 4, 5, 6. Okay, and this will again lose a molecule of water, that is this OH, and this H will go out in the form of a molecule of water to ultimately give us this guy, benzene ring C connected to benzene ring, double bond N, because we have lost a molecule of water here, therefore there will be a double bond, which is connected to N, which is connected to double bond CH, which is connected to this benzene ring. Okay, so this is our T, very important. Okay, so now we know Q, R, S, and T. So therefore, let's look into the options one by one. Option A says that S on warming with ammoniacal AgNO3 results in the formation of silver mirror. Okay, so S is benzene ring, C double bond O, benzene ring, C double bond O, H. Okay, so we should know that both aliphatic and aromatic aldehydes reduce Tollens reagent into silver mirror. Okay, and S is an aromatic aldehyde because CHO is connected to a benzene ring. So therefore A is correct. That is, statement A is correct. So S on warming with ammoniacal AgNO3 results in the formation of silver mirror. Now coming to statement B. Statement B says that Q on treatment with Cl2 excess in the presence of UV gives gamma-xane. Okay, so Q is our benzene ring. In presence of sunlight, benzene adds 3 molecules of chlorine to form benzene hexachloride, that is BHC, or gamma-xane. It is also known as gamma-xane. Okay, so with respect to reaction, I can write benzene ring plus 3 molecules of Cl2, or we can also write Cl2 in excess, H nu and 500 Kelvin. So it will give us HCl, 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 H and Cl. Okay, so this guy is known as our, benzene hexachloride, BHC. It is also known as gamma-xane. It is also known as gamma-xane. Okay, so therefore B is a correct statement. Coming to C, statement C, it says that T is a heterocyclic compound. Okay, so the structure of T is benzene ring, C double bond N connected to benzene ring, N double bond CH. Yeah. So cyclic compounds containing one or more heteroatoms. Okay, so heteroatoms are atoms other than carbon and hydrogen in their rings are known as heterocyclic compounds. Very important. Cyclic compounds containing one or more heteroatoms. So heteroatoms are atoms other than carbon and hydrogen in their rings. So they are known as heterocyclic compounds. Okay. So therefore C is a correct statement because you can see it contains N in the ring. N is there in the ring, which is a heteroatom. Okay. So therefore C is correct. Coming to statement D. Statement D says that R on acid catalyzed intramolecular cyclization followed by treatment with ZnHg HCl gives 9,10 dihydroxyanthracene. Okay, so R is this guy, benzene ring, C double bond O, benzene ring, C double bond O, OH. Okay, so this in the presence of H plus. Okay, so in the presence of strong acids like HCl, H2SO4, HNO3, carboxylic acids act as weak bases. That is, they accept H plus. Okay, important. In presence of strong acids, carboxylic acids act as weak bases. That is, they accept it accepts H plus. Okay, so to show that, I will write OH in this fashion. O has two lone pairs, so it will share these lone pairs with this H plus. Okay, so it will form benzene ring, C double bond O, benzene ring, C double bond O, O, H. It has formed a bond with H, one lone pair, and there will be a positive charge. Okay, so O bearing a positive charge, that is this guy, takes the bond pairs of electron, that is these electrons, and it goes out in the form of water molecule. Okay, resulting into, so there will be loss of a water molecule, so it will result into benzene ring, C double bond O, C double bond O plus charge. Okay, and obviously this benzene ring has an H here. Okay, so I will show it in this way. So this carbon takes these electron pair, so I can show that in this fashion, C double bond O. So it will have a lone pair and a negative charge, and an H plus goes out, and that these lone pairs will be shared to this positively charged carbon, ultimately to give me benzene ring, C double bond O, benzene ring, C double bond O. Okay, so this is the product that we get after we do acid catalyzed intramolecular cyclization on R. Okay, then this guy is treated with ZnHg HCl. Okay, so we should know that carbonyl group is reduced to methylene group in the presence of zinc amalgam and concentrated HCl. That is, it is the famous Clemmensen reduction. Okay, so I will write it down. Carbonyl group is reduced to methylene group. That is the CH2 group. Okay, so therefore, with respect to reaction, I can write. So this guy, C double bond O, in the presence of ZnHg HCl will give me benzene ring, CH2, CH2. So this is the final product that we get, and this is not, so this is not 9 comma 10 dihydroxy anthracene. Okay, so to draw the structure of 9 comma 10 dihydroxy anthracene, first let's see the structure of anthracene, which looks like this. There are three benzene ring fused to each other. So 1 2 3 4 5 6 7. So we start the numbering in this fashion: 1 2 3 4, be careful, 5 6 7 8, then 9, then 10. Okay, so this is our anthracene. Okay, and 9 10 dihydroxy anthracene will be, so normally there is one hydrogen here in 9 and 10 positions. So 9 comma 10 dihydroxy anthracene will be, instead of, instead of hydrogen we will have OH here. So this is the structure of 9 comma 10 dihydroxy anthracene. Okay, so the structure that we got, this is not 9 comma 10 dihydroxy anthracene. Okay, so therefore D is a incorrect statement. Okay, so therefore the correct statements about Q, R, S, and T is A, B, and C. Okay, thank you.